Let's look at an application of exponential decay, and in particular, radioactive decay. So, uh, think about if we have this radioactive substance, it's unstable and it decays and gives off energy as it's decaying toward this more stable substance. And the way we measure that, the way we talk about how fast it decays, is we use this term half-life. In other words, we would say that the half-life is how long it takes for half of the substance to decay. So for example, let's suppose we have 96 grams of this radioactive waltium. I just made that up. And the half-life is 10 years. Find a model for the amount of waltium over time. So here's what we've got. We start off with 96 grams. In 10 years, half of it's gone. Okay? It takes 10 years for that to happen. So when t equals 10, we've got 96 times 1/2. Now, in 10 more years, well, half of this is gone. So we have this amount times 1/2. Okay? So we get 96 times 1/2 to the second. Okay, after 30 years, okay, there's another 10-year period. Now we're going to take half of this, right? Half of this right here. Okay? And so forth. So we go to 40 years. And now we take half of this right there. And we've got 96 times 1/2 to the fourth. Okay. Now, you can see a pattern here. You notice that every 10 years we're going to multiply times 1/2. So how might that look? Well, think about this one. Think about the initial amount, 96, and then we've got 1/2 raised to a power. Now notice what I did was I put t over 10. See? So when t is equal to 10, what I have here is 96 times 1/2 to the first. Like this right here, see? Now, when t is 20, this up here is 20 divided by 10 is 2. So I have 96 times 1/2 to the second. See, like this right here. See? When t is 30, this exponent is 3, and I get this, see? 96 times 1/2 to the third. So this right here is my model for the amount of radioactive waltium that I have over time. So in general, we could say this. We could say, well, let's write the model this way. We take the initial amount, right here, A sub 0, A naught, times 1/2 to the t over the half-life, whatever the half-life is. Here it was 10. It could be 1,000, whatever. But this is the model that we can use just as an example of exponential decay. So let's suppose that we have 100 grams of a radioactive cornelium. Once again, I made this up. It's no such element. And the half-life is 30 years. Find how long until only 20 grams remain. Well, first thing we want to do is we want to write the model. Using what I just showed you, we take the 100, that's the initial amount, 1/2 to the t over 30, because 30 is the half-life. Now we want to know, this is the amount of the substance left. Now we want to know, when will this A of t equal 20? Well, a good way to figure that out is just look at the graph. Notice we have the model here, 100 times 1/2 to the t over 30, that's this. And then we have y equals 20, see, 20 grams. So we're wondering, well, when does this equal 20? We'll just find the intersection of these two curves, this y equals 20 and this 100 times 1/2 to the t over 30. And you can see the intersection is right here at 69.658. That's when you have this amount, the 20 grams.